And I did not start recording. All right, so anybody who's here, I want you please to speak up. Can you explain how you did this work? Sherbel maybe can speak up. Yes. Yes. Okay. Not really, just tell me. Yes, Ramza, I was reading you. So tell me, did you get the same answer for the slope, Excel versus calculator? Okay. Okay. And the slope was actually equal to the resistance. This is what you're saying. Okay. What was the choice of the x-axis and the y-axis in your case? Okay, perfect. And let's say I take you to be my x-axis and I to be my y-axis. Do you think you will have any change? So the slope will not be the resistance anymore. What will it be? So, yes. Okay, so the slope is gonna be 1 over r. So James Tannous is saying that he cannot hear us. James, I assume everybody else can. It could be an issue from your side. James, try to go out and in again. Okay, it could be that you need to settle in your audio. Okay, James? All right, so yes, so if we plot I versus U and not U versus I, the slope will be 1 over R, and yet you can find R by doing 1 over the slope. So that was one of the questions you had to answer, and you did it well. The final question you had to cover was the one at the end, this one, which is find the error on your slope. Anybody other than George would like to speak up about how we do this one? Maybe Sherbel? Is Sherbel? Okay, I would love to hear you. Just let me close this. Okay, somebody's calling someone here. My kids, I need to close it, otherwise it will be bad on my ears. Okay, so please explain. Yes. Yeah, the Linus function. Do you think it was easy to follow for you? I know this function and I believe it's not straightforward. Do you think it's worth it to learn it? Okay. Are you willing to explain this to the class? Do you think your friends would be happy to know how you did the work? Maybe not today, some later time. Are you willing to explain? Okay, George, are you willing to videotape yourself while explaining it and maybe share with me and I can share it with the class? Yeah, anytime, anytime. So the Linus method has been going on and off for many semesters. A lot of students would love to use it. Personally, I decided not to share it with you. I thought it would be somehow confusing for you. But George used it and he believes maybe it would be worth it for us to give it a shot. Otherwise, George, did you try any other method to compare with the Linus results? Okay, did you try to get an answer or was it time consuming? Zero plus or minus 0.3, I assume ohms. By the way, I assume that you converted the milliamperes to amperes, right? For you to get ohms eventually, or didn't you? Okay, so this is a tiny mistake. I'm happy you did this mistake. At least now we know. All right. Okay. Anybody in this room would like us to videotape the procedure step by step on finding the error on the slope? Okay, please let me know in the chat or maybe privately later on, email me saying we don't know how to do this, so I can do it step by step for you. Okay, maybe do it anyway. What do you think? Yes, please. All right, Ryan. So I'm gonna do that. Also, I remember that I promised to show this, although everybody has good answers. Um, I did the error on R. Maybe not for you. For you, you had the example where it was A is equal to G sine alpha. Some students are still not confident about it. So I'm gonna videotape this one and the other one. And George is gonna videotape the Linus method and send it to me, okay? All right, shall we close data analysis? But again, we can ask and go back to data analysis anytime you want. This will stay with us throughout the semester, okay? Yes. Um, yes, Ryan has an important question too. Go ahead, I will answer Ryan in a moment. Yes, Joe. Okay, so try not to round at all until you reach the final answer. So if I were you, I write the slope with as many significant figures as I can. Then I find the error, all the steps I do no rounding whatsoever. That's why Excel would help. And at the end, you round your error to one sig fig and then compare with the slope, round the slope accordingly. Okay, so try to do minimum rounding until the end. Yes, Joe. Yes, if you find it difficult to round, because a lot of students find this confusing, write it as in scientific notation. So 238 can be written as 2.38 times 10 to the 2, and then rounding it will look easier. All right, back to you, Ryan, concerning Excel. Do we have Excel during the exam? No, I think we will not have it unless I can find a way for us to have an exam that is computer based. I'm afraid that LAU may not allow us to eventually. All right, which means we should always back our, I don't know, methods on our calculator, and that's sad, and I don't like this. Okay, so Ryan, I don't have an answer for you yet concerning the fact if we have Excel during the exam. Let's try to have it, okay? And I'll be working towards this because I know you will learn to do many things on Excel, and it's a shame not to have a platform like Excel during exams. Now let's focus on the first 4 lab reports before we reach the midterm. So, okay. All right, so back to you. So we're gonna follow the theoretical background that is very simple. Uh, this is basically grade 11 material, so you may know most of it. The equipotential line may have a difficult approach though. And then I'm gonna move to show you the experiment that I recorded and eventually the lab report to explain what you need to fill in, okay? Lab 1, Equipotential Lines and Electric Field Mapping, that's the title. Physics 306, it's Lab 1. This is all you need to know. By the way, you need to submit the work anytime before next Monday at 11. Okay, I will explain how, which means if you can finish it tomorrow, after tomorrow, please do so. Don't wait until the deadline. So, all right, so I need your input here. What is a field? We talk about electric field, we talk about gravitational field, we talk about magnetic field. What is it? How can we test it? Anybody would like to speak up? So again, want to see the names. Yes. Is Fadel here? Or Mia Maria? Francesca, I saw Francesca's name a few minutes ago. So please speak up. Yes. Okay, so Francesca, back to you. How do you explain a field? What is a field? Yes, what is a field? The question is written on the screen. Okay. All right, let me remove my earphones because I think your answers are not going to show up in the recording and you have interesting answers. Can you still hear me? Yes? Maybe you can hear some background noise. If it's really noisy, let me know. All right, so Francesca's discussing fields could be like electric field, magnetic field. We cannot smell it, we cannot see it. Francesca, how do you know a field exists around you right now? So how do you know a field exists around you?
Hi, doctor.
Hello. Yes,
How are
Michelle.
you?
I'm good.
Doctor, my network connection wasn't that well. I had to fix it. Did we
Okay.
explain anything in the 13 minutes?
Yes, we discussed many things. Please watch the recording to check it out. Okay, Michelle? All right, back to you, Francesca. I'm sorry for the interruption. So you were explaining what a field is and how it you were trying to describe it. Can you please try to tell me how do you know if there's a field around you?
Like, for example, if I want to see if we have a magnetic field, I could get metal or another magnet to see if it will move or it will مثلا be attracted or repel.
Okay, what about the gravitational field?
Gravitational field, if I throw an object, it will go downwards. Like, I know that there is the gravitational field.
So I always refer back to gravity because gravity is something you experience since day one you were born, and you're an expert in gravity since you are 8 months old. You know, throwing all these pasta on the floor while your mom will go crazy. This is experimenting with gravity. And you just told me that you need a test mass to check if gravitational field exists, or a test magnetic object to see if the magnetic field exists, or a test charge to see if the electric field exists. So now back to the electric field. What is an electric field? Because this is what we care in this experiment. We basically need to discuss the following. Going back to gravity, you have a source of mass and you have a gravitational field that is inward and radial. For the electric field, you can have a positive charge or a negative charge. This is a source, and the electric field is radial around it, outward in the case of a positive charge, and inward in the case of a negative charge. Now, for how you find the electric field, I can also compare the force of gravity to the electric field, and you already know this. This is the test. This is what you feel if you are a test, and that's the strength of the field, which is this one. It's related to the mass of the source and the distance squared. For the electric force, it's the Q of the test charge, and the electric field, which is related to the source and the distance squared, okay? Now, if I give you different types of sources, and let's say that A is a source, B is a source, electric, can anybody tell me if the source in this case is positive or negative?
Positive.
Obviously positive because the electric field is outward. And which source is stronger in magnitude, A, B, or C?
C.
All right, so the number of lines, of electric field lines, is proportional to the strength of the source, true? And this is the case where you need to draw the electric field lines when you have 2 point-like charges facing each other. By the way, what you see here is not the electric field E1, neither E2, it's E resultant or E total. Okay, so what you have in here, this one is not E1 and this one is not E2. It's the resultant of both sources together. And you know this from grade 11. Please let me know if you have a problem on this level. Now, this is a very important discussion for us. You have a negative source. It can be an ion like SO42 minus, and you can see an electric field created around it that is radial and inward. I'm gonna place a proton. Do you see this? A proton. Let me underline and put in bold. I'm gonna place a proton at position A. I need somebody to tell me what happens to the proton. Do you think it will move? So I'm gonna discuss the motion using simple common, yeah.
The proton will move towards the negative charge. They will attract.
Okay, so the reason is plus and minus attract. The proton will move to the minus. Any other reason you can think of? or to explain things differently, because eventually it's the same reason?
The electric field on F equals QE, so the test charge is positive, so F and E are same direction.
I love this, George Michael. So George is saying, since the proton will feel an electric force, and the electric force is pointing parallel to the electric field. Yes, since the force, George, you're moving and you're noisy. Yes, so the electric force is parallel to the electric field, since the test charge, that is a proton, is positive. All right, so the proton placed at A will move towards the source. If the proton was placed in B, it will move towards the source passing through C. So as the proton is moving from B to C, you have a potential change between B and C. B and C are 2 points that they have a different potential. So the potential at B is different than the potential at C. I need somebody to try to explain to me, do you believe the potential at B is greater or less than the potential of C? Maybe start with a definition of potential. Anybody can discuss the potential of A, B, and C?
It's B is greater and it's subjected to repulsion by C. Repulsion increases the energy of a system.
Yes.
Yes, so B must have a higher potential energy than A due to the repulsion that occurs along with the same attraction.
Okay.
يعني they're both undergoing attraction, بس عم يزيد على البي repulsion in the C, where repulsion increases the energy of a system.
All right, I agree with Michelle. As you go away from the negative source, the potential increases. So the potential of B is bigger than the potential of C. Maybe we can type it down for us to keep it. So the potential at B is greater than the potential at C, right? And the proton placed in B would want to move from high potential to low potential. This is important for the proton. So the motion always happens from high potential, right? From high potential. By the way, I'm not on my desk. My kids just threw me out because they have class. From high potential to low potential, and I hate this. I need my desk. By the way, I'm not on campus today. I had to stay here. So high potential to low potential. Anybody can compare the potential of A to the potential of B. A and B are at the same distance away from the source. How do you compare them?
Doctor, if we say that V is KQ over R, so if they're at the same R, same Q.
KQ over R. I love this. Yes. So they
yes, exactly. At the same distance, the K is constant, and then Q, they're subjected to the same field, the electric.
Exactly. So we say the potential at A is the same as the potential at B. Since they have the same potential, the proton cannot move between A and B because the proton has to move from high potential to low potential. I'm talking about the proton. If I place a negative charge, it will move opposite. It will move from low potential to high potential. So A and B are at the same distance away from C, and therefore they have the same potential, and therefore no motion is going to happen between both. And I can also add that any point that is at the same distance away from the source has the same potential as the other. So this line is called the equipotential line. It's a line that is at the same, in this case, same distance away from the source. And all the points of this line, they have the same potential. We call it equipotential because they have the same potential. Now, another question. What is the potential difference between A and B? Anyone? Potential difference between A and B.
Is it zero?
It is
because they are equal.
Can you think of a different name for potential difference? Tab, do you know a measuring tool that would measure potential difference?
Voltmeter.
Voltmeter. So I'm gonna call it a voltage between A and B. just to make it look and sound easier. So the voltage between A and B is gonna be 0. All right, now back to the lab. All we have is a voltmeter, and we need to find all the points that would give you a voltage equal to 0. Now, can you think of a relationship between the black lines and the red line? Can you see some relationship? Like if I give you the red lines, will you be able to deduce the black lines? Okay, so the answer to this question is they're always perpendicular. Okay, so the red line is perpendicular to the black line. So in the lab, we're gonna find the red line, which is the equipotential line. I will show you how you do the map, and you deduce the black lines using the simple fact that the red is always perpendicular to the black. Why perpendicular? Because if you move parallel to the black line, the potential has to change because you're getting closer or away from the charge. But if you move perpendicular to the black line, the distance is gonna be constant, and there's no change in the electric field or the potential difference, the potential. Okay, now let me show you some weird shapes. I mean different cases where you have a point-like sources or not. In this case, you have a flat surface. You have the electric field lines in blue, the equipotential lines in black, and you see the different shapes, and you see they're always perpendicular, and you can see curvature is happening on the black lines, and some density of lines is happening on the blue lines. So these are different. Also, this would show you some electric equipotential lines. So you can call this the potential, the equipotential line that represent 3 kilovolts, a constant potential. This is another constant potential, 1 kilovolts. The 1 kilovolts per se means nothing. It's 1000 volt with respect to a reference. The reference is here. This is the reference. It's where the voltage is, not the voltage, the potential is equal to 0. And you see different shapes and different curvature depending on what source you have. All right, so that's it for the theoretical background. As you can see, it's mostly descriptive. I did not use any equation and any value. Now I'm gonna move a little bit for maybe the lab report first, then the experiment itself, okay? I'm gonna send you the lab report alone, although you already have the manual in full. So maybe separate lab 1 from the others for you to be happy and comfortable. By the way, you can jump by clicking, no, only on the doc file, not on the PDF. Okay, so what are you supposed to do? You move to lab 1. Yeah, which is here, experiment 1. You read the objective, the equipment needed. The theory, as you can see, is basically something very similar to what we discussed. The difference is I showed you some gravity related. So the height in this case is the potential. So if I need to compare gravity to electric field, the height is the potential. So the height is for gravity, what potential is for electricity. And you see the equipotential lines are the line of the same height, you know? So you see these on the map. If you don't understand what is a topographical map, gravity related, don't worry, I was trying to make your life easier. Now the procedure, you can read it, but I'm gonna show you the procedure in a video. And these are what not to do related to the procedure. Now the lab report, you will be given a map. So when they ask you map the equipotential lines on a graph, I have to do it for you. So I'm gonna give you the graph. You do item 2, sketch the electric field lines, and answer question 3, then answer questions 1 to 9. Okay, these are simple questions, some of which are related to the map, some of which are theoretical questions. How do you find the answers to these questions? You can use your textbook for the course, your slides for the course. Try to read online some related theory related questions. Some questions like, is it possible for 2 different equipotential lines or 2 lines of force to cross? This is a famous question. So think about it. Try to give a reason why your answer is yes or no. It could be an example or a counter example. Let me know if you have any difficulty on that level. Okay? Shall we move on to the experiment and the recording? No, Ryan, you're gonna be individual. Thank you for your question. Each student has to do the work alone. This is good and bad at the same time. It's good because you focus on your schedule, your work, you finish on time, you don't rely on other people. It's bad because maybe at some point you will have more work to submit, but I don't think so because the labs has been modified. And since most of the work is done by your instructor, which is me, like the experiment itself, all you need to do is answer the question. So I'm gonna be your partner if you need me to, Ryan. Okay, let me save this one. Okay, Ryan, save this one to send it later to you and close it for the moment. And let me move to the recording that is here. The recording is already on YouTube. I'm gonna send you the link. I divided the movie into 2 parts because I don't want you to be frustrated watching something that is 10 minutes long. At least you can watch one. All right, so this is like 2 minutes long to describe what it is, and we're not gonna watch it all, just quickly. Hello everyone, welcome to the first experiment we have for Physics 306. It's called electric field mapping or equipotential lines. All right, so let me get the camera closer to show you the different equipment we have. All right, so the equipment needed, you need a multimeter. This is the test multimeter I will be using on the scale. So basically this multimeter is to find the voltage or the potential difference. In other words, finding the different zeros, okay? You need 4 banana wires. So you can see 2 banana wires already attached to your power supply. So these are regular wires, but the terminal looks like a banana. I like them, although other instructors do not use them for this experiment. I actually like them because they do not poke the conductive paper. I will explain what is a conductive paper, and I don't want to poke it because poking it will destroy it in a way. And another 2 banana wires that I will be using for my multimeter. By the way, this is the power supply because you won't be able to see it. It's a DC power supply. You can control the current and the voltage as you may. You have a positive terminal and a negative terminal, the power on-off button, and it's connected to the mains. What else? This is a board. It's a cork board on which I'll be using a conductive paper. This conductive paper is supposed to be brand new, so it shouldn't be poked anywhere, and this is the case. So I'm gonna take the conductive paper. So that was the equipment needed. Now the procedure. I'm gonna place the conductive paper on top of the board. I need to make sure I have conductive pins attached to my wires, okay? I'm gonna poke the paper rigidly at the extremities of the paper. All right, so I just poked, I've chosen 2 positions, usually at the extremity of the paper so I can have some space. Now when I put the power supply on, I would create a positive terminal. I think the red was positive and the blue was negative, like 2 point-like sources facing each other of opposite charge. So how do you think the electric field between the 2 lines would be? Anybody knows how to describe it? Yes? So I have a positive charge. Yes.
Would it be resultant in some way?
Yeah, so what you would see a resultant electric field. Can you describe it? How does it look like?
Isn't it dependent on which charge is greatest?
The 2 charges will be equal and opposite. One negative, one positive.
I don't know how it's gonna look like.
Okay.
Doctor, isn't it the positive would go towards the negative?
Yeah, it will be maybe not wise to describe it in words. Maybe show it on a figure, and we already have an example on those slides. This case, right? You will have this case. You will not see the electric field, and there's no way to test it with the equipment we have. You would expect to have a map that looks like this one, okay? So your equipotential lines will look like this one, and you can see the line in the middle to be vertical, not really vertical, straight, because the whole thing is on a desk, horizontal. So this is one equipotential line. Then you see that the equipotential lines will happen to curve themselves as you get closer to the source and to the other source. So this is what I'm gonna find with a voltmeter. So if I put the voltmeter between this point, let me use draw to explain, maybe use red because this is tiny. If I put the terminal of the voltmeter between this point and this point, I get 0. And between this point and this point, I get 0. Now, how can I use my voltmeter to find all the zeros and draw the map? I hope the video is clear, I know, but I found it very difficult to explain through a video. Let me see the next video before I leave you. So let me know if it was clear or not, and stop me if you have questions. One pin is connected to the red banana wire that goes into the minus terminal, and one pin is connected to the blue banana wire that goes into the positive terminal. The power supply is off, so there's no potential difference between these two points. But when I put the power supply on and I see a 20 volts displayed on the screen, I would know that I just created 2 point-like charges. The potential difference between these 2 point charges is 20. So I know the difference is 20 volts, but I don't know what does each represent. It could be positive 10 volt, negative 10 volts, you know? It could be, I don't know, 11 volts versus negative 9. I know the difference is 20, and this is what I care about. My job is to use the voltmeter, the multimeter on volts, to be able to try to do some measurements. I will use my voltmeter on the scale 20 volts because 20 volts will give me 2 decimals. I will not be measuring voltages more than 20 volts, more than 2 volts though, so I can simply use 2 volts as well. But 3 decimals for me is a lot of precision, and I don't need this, knowing that the experiment is not super precise. So a scale of 20 volts or measurements of 2 decimals are enough. I'm gonna take these wires, the red one, plug them into the COM and the V plugs. And some instructors would love to keep the red for the positive. In my case, I don't mind, especially that in the lab we have brown and yellow, and like just follow up on your polarities. I will put this to the camera, hopefully you can see it. Okay, and I'm gonna be measuring the voltage or the potential difference across my paper. If I measure the pins, the potential difference across the pins, I should get something very close to 20, and I'm not because my power supply is off. I will put my power supply on, and I can see a measurement very close to 19.9 volts, which makes sense because these are the terminals of my power supply. Now, if I measure the potential difference across 2 different points on the paper, I can see that it's a non-zero measurement, which means these 2 points do not belong to the same equipotential lines. Remember, points do belong to the same equipotential lines in case they have the same potential. Therefore, the potential difference is 0. Now, my job is to find equipotential lines and to be able to map them. So I'm supposed to find 2 points or many points belonging to the same equipotential line, therefore having the same potential, therefore having a potential difference equal to 0. All right, so as you can see, I'm doing some repetition in here and I'm explaining very slowly because many students previously had difficulty understanding how to go on with the procedure. Happily, they could try. In your case, you cannot try at the moment until I see you. So, which means that's why I want you to try to watch the video many times, okay? With my red terminal being my reference exactly in the middle of the paper, and I'm gonna try this point. Does it give me 0? No, I will move it a little bit to the left. to get 0. I found my 0. I write down the coordinates of this point. I'm gonna move now the blue terminal 1 centimeter up. Is it a 0? No. I will move it a little bit to the left. Bingo, I got 0. I will mark my coordinates. All right, so in this experiment, you're supposed to be ready with another paper that is very similar to the black one. By the way, the grid lines on the black one are 1 centimeter spaced. And I think the smallest subdivision is 1 big centimeter. That's why it's not super precise. And therefore, that's why the multimeter should not be very precise. No needed, not needed at all. So my job is every time I find a 0, I should mark on the other paper my 0 before I trace my equipotential line. So as you can see, I'm gonna and so forth. I'm gonna find all the zeros, mark them on a different paper where I can see the coordinates. It will be a duplicate of this conductor paper. Done with my first line. Now I will actually move my reference 1 centimeter to the left and do the same thing again, trying to find my zeros. 1 centimeter up, 1 centimeter up at a time. Move the reference until I get very close to the source where I can see that a point just above the reference will not give you 0 at all. It will give you a value very far away from 0. This is where you're supposed to be moving your blue banana wire to the left and find the 0 that I'm not being able to find. Where is that 0? Okay, let me try again. Okay, I just... All right, so in this case, I was passing 0. I just noticed that it went from negative to positive. I should have stopped at 0. I think my paper is broke. That's why it's giving me weird results. So you do it slowly. I got to 0. I had to move 2 centimeters to the left. Okay, you see the fluctuation to get a 0 value, which means my line will end up being curved as I get closer to the source. Okay, so I move my reference 1 centimeter at a time, my blue terminal up and down to find the 0 values for the potential difference. Well, then I would use my reference to move it 1 centimeter at a time to the right side and be able to find the different value. So that's it. All right, so I'm gonna share the videos with you. I hope that the procedure was easy. I know the procedure, if I had to do it live in front of you, would be a little bit confusing. So how about recording it? But I'm gonna share with you the map I did, which looks exactly or something very similar to this one, only the black lines, and you fill in the lab reports. Do you have any questions? I think that's it.
Yes, Dr. Aya.
Yes, please ask, Ryan.
With the red banana plug, you're just moving on the axis that's linking the positive to the, and then with the blue, you're moving up and down.
Excellent question, Ryan. I use one of the terminals. Let's assume the red to be my reference. And the blue terminal would be the one finding the points. When I finish one line, I move the red and find another line again. So I'm using the red to be my reference. Otherwise, it will be messy and I won't be able to tell how the lines are spread around the paper. So fix one terminal, let's say the red, move the blue. You draw the line, you're done. Now move the reference again and then move the blue. So I move one reference at a time. So keep the reference constant and move the blue. When I finish the line, I move to a new line, meaning that the reference would move. Do I make sense?
Yes, I understand you.
Yeah.
But does it matter which one, if the red or the blue? Well, no.
It doesn't matter because I'm finding the zeros. Let's say I want to find a potential difference that is positive 2. This is where I have to monitor all the polarities. Since in this experiment, I only need to find the 0, I don't really care about plus and minus. And you see throughout the procedure, I've never looked where's my plus and where's my minus. Okay, because my job was to find the 0. Positive 0 or a negative 0 doesn't really matter. But usually we take the negative terminals to be references. So the other one would give you a positive answer. Okay,
thank you,
originally this lab was different. Originally, you had to put the reference on one of the terminals of the power supply and find all the points that would give you, let's say, 1 volt. Then find all the points that would give you 2 volts. Then find all the points that would give you 3 volts. But experimentally, it was very difficult with all the fluctuation. So finding zeros is easier experimentally. You see?
Yes. Thank you, doctor.
So that's why I went through the procedure in the manual and I changed it all to explain that we want to find the zeros. I hope it will not be confusing for you. Any other question? All right, so you're gonna expect from me the slides. Okay, now let me show you my my Blackboard, how it looks like. You're supposed to go here and go into lab 1. All you can see right now is where to submit. So this is where you will be submitting your work. Please submit the lab report section only. Do not submit the manual section. The lab report section is your answer and the questions. Okay, you're supposed, I'm gonna fill this section with PowerPoint, the 2 videos we just got, and a picture of the map. You can take the picture of the map, insert in your document, and draw on it because you're supposed to be drawing the electric field. And that's it. You have a week to submit the work. During this week, please email me any question that comes to your mind. Okay? It's gonna be our first trial and our first graded work. If we see that we need to modify anything in the procedure and the dynamics of us, communicating with each other, we're gonna do that with lab 2. Okay, lab 2 is easier procedure wise. The lab report is longer and it has more data analysis. In this lab report, you will not be required to do any average, any computation of the uncertainty because it's gonna be mostly descriptive. So we can put lab 0 aside for the moment and focus on the procedure. But in lab 2, we have to go back and use most of what we learned in lab 0, okay? Any other question? All right, I'm gonna stop recording and you are free to leave. Unless you have something to say, please stay behind.